We are electrical and computer engineering students at Oregon State University.
We are in junior design in winter term of 2019.
And for our project, we built an adjustable linear power supply. I'm Shanti Stewart, and I worked on prototyping and documentation.
I'm Jordan Baxter. I worked on circuit design, 3D modeling, and product testing.
I'm Zach Pelster. I worked on prototyping and assembly.
Our main engineering requirement was to output voltage with a range of 2 volts to 12 volts at a maximum current of 700 milliamps. Also, we were required for the voltage ripple at the 12 volt output to be less than 500 millivolts. We were also required to use bipolar junction transistors to implement the feedback loop which controlled the output. Here is our block diagram for our project. Our product was supplied by a DC benchtop power supply. In order to display the output voltage, we used a LCD voltmeter, and in order to display the output current, we used a LCD current display. We powered the LCD current display by a separate voltage source because it was recommended by the manufacturer, and also because the current display had a minimum voltage input of 4.5 volts, which would not be met in some cases of the output voltage. Here is our interface definitions, which provide a little bit more detail about the relationships between the different blocks. There are a couple points I'd like to highlight. First of all, the input voltage to our product had a maximum of 15 volts because the transistors could only dissipate so much power. Also, our power supply output voltage was 2.0 volts to 12.5 volts. And the last two interface definitions simply describe the displays of the voltage and current ranges.
Let's take a look at our schematic. In our forward path, we have the voltage across R1 driving the base of Q2. The emitter of Q2 drives the bases of Q3, 5, and 6 in our Darlington pair network. These three BJTs feed into our current limiting circuit. This current sense resistor attenuates the current gain past 1 amp. That goes to Vout, which goes through a low-pass filter with a corner frequency of 500 kilohertz. In our feedback loop, we have a voltage divider circuit with our two potentiometers to adjust output voltage. That feeds the base of Q2, which drives the voltage drop across R1, completing our feedback loop.
Here we have our Vout and Iout versus our potential. In the Iout versus our potential graph, we have our 5 ohm, 10 ohm, 15 ohm, and 20 ohm load resistances. It can be seen that each of these lines are linear, with the exception of the 5 ohm, which begins to peak at around 1.1 amp, and in the case of the Vout versus our potential graph, around 12 volts.
Here's our low-pass filter characteristics at R load equal to 20 ohms. Here's our potentiometer at 10K, 14K, 16K, and 20K. As you can see, we have a little bit of peaking around 500 kilohertz. That's due to the intrinsic capacitances in the BJTs. Luckily, our engineering requirement is that our voltage ripple at 12 volts be less than 500 millivolts. And our 12 volt voltage ripple frequency is approximately 10 megahertz, which gets attenuated by 40 dB. Let's take a look at our drawings. We needed something that we could attach everything to once we built the supply, have all of our displays in the same place and not hanging around. So we designed this 3D printed skeleton that our power supply could be mounted on. Here's the skeleton on its own. We have current and voltage displays. Here's the back side of the skeleton with our current sense, voltmeter, and power supply with the battery pack on the bottom. And here's the skeleton with everything in the front.
For our assembly, we took the path that most engineers take by developing our circuit on a breadboard first to confirm that it works as expected. After confirming this, we developed the proto board and implemented it into our final product.
let's take a look at our data analytics. This orange line represents our efficiency, and this blue line represents our voltage ripple across a vector of output currents with a V in of 15 volts and a V out of 10 volts. As you can see, our efficiency remains consistent throughout, approximately 63%. Our voltage ripple peaks at about 1.4 volts before hitting the corner frequency of our low pass filter characteristic and dropping significantly.
As part of our project, we were required to show our power supply operating at different voltages and currents. We were also required to show that our current sensor matched a DMM reading the same current. Here is our power supply outputting 12 volts at approximately 400 milliamps with a voltage ripple of less than 2 millivolts. Here is our power supply outputting 2 volts at approximately 700 milliamps. There was no requirement for voltage ripple at this output voltage, so it is not displayed. For our next steps, we would like to add a larger capacitor to lower the corner frequency across the low-pass filter. We would also like to add heat sinks to aid with power dissipation across the BJTs. Lastly, we would like to do a fabricated PCB for a more professional look.